its topological space of complex points, right? And then you can con-extend this. Now we can work with pre-sheaves of. So anytime I say pre-sheaves, I mean simplicial pre-sheaves. I'm kind of working in the infinity category context. So,
maybe a
question.
Type.
Yes, right, sure. Right, you can take the con extension of this functor into right. You can view this as a space. So say left con extending this. You get a colimit preserving functor into spaces, and you can then stabilize this and get and what does it mean to stabilize this? I'll just use the same notation for these two functors. Essentially, I'm only going to be using this bottom one here. So you can, what's the stabilization of this? This is just pre-sheaves valued in spectra on this category. So I'll use this notation, pre-sheaves valued in spectra on schemes of finite type. C. Okay, so this is somehow one ingredient of this construction. And the next is we want.
So maybe there's a confusion. So the first functor, the target, you view it as an animal, right?
Yeah, I mean, you can take sing of this. Yeah. Yes, you're viewing it as a space. Yeah. Yeah, no condensed thing or anything. Yes, so then, right. Now we want to apply this to a specified pre-sheaf. So given, right, the point is we want to define an invariant of complex linear stable infinity categories. So start off with a category C, and this is, I'll just use this notation, idempotent complete stable infinity categories. So, right, we start off with this. We get a pre-sheaf on schemes of finite type. Use this notation. This just sends a scheme X. Right, so let's write this. Right, such that X, right. So X is sent to the spectrum, which is the K-theory of C tensor over the complex, over the unit, which is complex numbers with perfect complexes on X. This is a perfectly reasonable pre-sheaf of spectra. That's the K-theory pre-sheaf. And it's an object here, so you can hit it with this realization functor. And this will be the definition due to, essentially due to Anthony Blanc, of semi-topological K-theory. So this is the first step to defining this invariant. So this will just be the realization of this pre-sheaf. And proposition, what happens when you C is the unit, C linear DG category, is that the semi-topological K-theory of C is just KU, little KU, connective complex K-theory. Right. So essentially, yeah, because K-theory is lax-monoidal, this assignment to the K-theory pre-sheaf is itself lax-monoidal. This will be strongly symmetric monoidal. All this means that, right, so all this means that for any C linear category C, you'll have a module over little KU. So you can invert the bot element. So and this is the definition. Use this notation. Right. So, and this lives in modules over periodic KU in spectra. So yeah, this is a functor from. So we obtain right. In fact, I'll just say from now a localizing invariant. valued in KU modules. I'll just use that. Right. Okay, so let me present another somehow more modern way of defining this invariant, and it's somehow more motivic. So right, this is the classical way to define this, in quotes. Mm-hmm. It sends, well, you have this notion of right, you have a notion of exact sequence of DG categories. This is like the cone of this map, and it said this. So an invariant sends this. You can view this as like a fiber and a co-fiber sequence in this category of idempotent complete DG categories, and F is localizing if it sends this to a co-fiber sequence of spectra. Or fiber sequence.
Do you also claim that it's a filter calling preserve?
It does have this property, in fact. But, yeah. Okay, so this Motivic version. Let me say that by work of by work of, I guess, Blumberg, Gepner, Tabuada, but also in this case by work of Roballo, and also studied in further depth by Blanc, Roballo, Tan, Vizzosi. There's a stable infinity category of A1 invariant non-commutative motives. And this variant that I'm going to describe here actually admits a nice comparison with commutative motives with SH. So this is this category SH. I'm basically working with the complex numbers, so, but this is done for over any commutative ring essentially. And you can think of this. I'm not going to spend so much time defining it, but we can think of this as right. There's a localization called the Nijmegen localization, which is compatible with Nijmegen sheafification, but it's not exactly this is localization on our category, but it's not it's not a sheaf condition. But so we can think of this as basically functors from let me write this way. Compact objects in idempotent complete categories, linear categories to spectra, and you apply this Nijmegen localization to so it's functors that are A1 invariant and satisfy a certain sort of Nijmegen descent, right? And this is exactly this category, and it admits a comparison with commutative motives, essentially because. Right. If you have a scheme, you could send it to its DG category of perfect complexes. This gives you an adjunction. So given any scheme, you can take perfect complexes. This gives you an adjunction with the left adjoint takes you from commutative motives to these non-commutative motives, and then it admits, and this is symmetric monoidal, and it admits a lax monoidal right adjoint, which I use this M notation for. And where? Here is idem, and then this is omega to denote compact objects. Right. Yeah, actually, so it's somehow it's like a covariant Uneda embedding. So you go technically there's a functor. So it's essentially just, so right, this will be a contravariant functor from categories. Right. Okay, so let me jump into this more motivic definition. So of this invariant. So we have this SH. Now there's a functor and one key property is that homotopy invariant K-theory is represented by the unit in this category. So so you get an object in this given a C-linear DG category. You get an object in SH C, and if you take maps to the unit, this is stable, so this will be a spectrum, and this is exactly the homotopy invariant K-theory of C. So it represents homotopy invariant K-theory. Or A1 invariant. All right, so construction then is the following. So this will be co-complete. This SH category will be co-complete. So even though we're originally just defining this for compact objects, we can extend and then get a functor from all idempotent complete categories. Now we can view this as a functor to SH to the opposite category, and then we take this internal Hom to the unit. So I use this notation for internal Hom. Then we get just a. This is a way, right? And then we take this right adjoint functor that I described here to commutative motives. So this is a way of assigning a cohomological motive to a DG category in SH, and as it turns out, this lands in KGL modules. Right. So yeah, it's somehow contravariant with respect to maps of schemes, and this is encoded by taking this duality here. Right. So now we started, like, to recap so far. We started off with a stable C-linear stable infinity category, and we obtained an object in mod. Right. So. In KGL modules. And now there's a very easy thing you can do. You just apply, we have Betti realization of, from SH landing into spectra. And so compose, which is essentially also induced from this functor of taking complex points. And this gives you topological K-theory on the nodes. This gives you something which is already 2 periodic, no need to invert a Bott element. And somehow I find this to be a nice perspective on this. So right, we can define the topological K-theory as to be also this. So I denote this composition. MC wedge. So okay. So now I've presented two ways of obtaining this. And again, this lands in Ku because KGL is sent. This will be symmetric monoidal from SH complex numbers to spectra, and it sends KGL to periodic Ku. So right, we get something once again in Ku modules. Okay, it's already that's the point I'm making. It's already inverted. Yes. Right. So now let's just step back and talk about some motivation for why one might try to define such a thing and make some computations with it. So the motivation I'll present, it comes from the theory of non-commutative Hodge structures. I'll sort of be heuristic with this, but so we can think of this as a Hodge theory. Well, maybe this is what deserves the parentheses. Hodge theory for categories. So recall, just we'll stick to territory, which is more familiar. Recall that for a complex vector space, the data of a Hodge structure is the following. I'll write it this way. One is a filtration. On H, and another is a rational or an integral structure. So in particular, you can obtain H as a base change from. So let's say that you have just an abelian group over Z, and you just tensor it with C. Or if it's a rational structure, it's a Q vector space, and right. So then you recover H with additional niceness properties. So the induced real structure obtains a conjugate filtration, but anyways. So, right, this is a classical Hodge structure, and in work of Katsarkov, Kontsevich, Pantev, a sort of a non-commutative or categorical generalization of this was proposed. Are there any questions, by any chance, while I'm erasing? No. Oops. Right. So, yeah, there's this non-commutative generalization which was proposed. I won't define it since it's somehow, it really will get us far afield. But what I will say is this is you can view it as a generalization in the following sense. If you have classical Hodge structures, and then you mod out, this is just it's a one category. I guess it's an abelian category. If you mod out by Tate twists, then this embeds into this non-commutative Hodge structure. So it actually is a sort of generalization, and one motivation that the authors had in coming up with this technology was to somehow display a link between homological mirror symmetry and Hodge theoretic mirror symmetry. But the key conjecture formed for this was the following. So let C be smooth and proper. C linear DG category. Then the periodic cyclic homology of C has a, right, and it can also be Z mod 2 graded, or 2 periodic. Let me write 2 periodic. So a 2 periodic in the sense that from Marco's talk of these matrix factorization categories, that's an example of a 2 periodic category. But right, it could be, it doesn't have to be, potentially 2 periodic or, right. So then periodic cyclic homology has a NC Hodge structure. And moreover, if it's Z2 graded and it can be refined to an ordinary ungraded or Z graded C linear DG category, then this is just an ordinary Hodge structure. So if it is Z graded, then HP it's an ordinary Hodge structure. What? I think the conjecture says it's a rational structure. Yeah. So, but yeah. So.
So when you say it has an ordinary Hodge structure, you mean lens? It's still up to date with, right? Lens.
Yes. Exactly. Okay. So remarks on how one can get this, and this is somehow why topological K theory was proposed. One, the first property, you want these 2 properties, right? The first property just comes from the fact that you have this degeneration of this non-commutative Hodge de Rham spectral sequence. I guess we're working over C now, so. So this which degenerates. Here is important. Well, I think there's some partial results in the 2 periodic setting, but let's just assume we're just not 2 periodic. So which degenerates by work of Caledon, and then revisited by Kilmatthew. But the thing that's still missing essentially is this the rational or the integral structure. And the proposal, due to or the guess, due to say Blanc, I guess Toen had this idea, others, is the following. It's just that all right, so that this rational structure, or perhaps even an integral structure.
Sorry, I have a question.
Yes.
How does 1 actually answer 1 there?
Somehow this gives a filtration on the groups. No. It's because this spectral sequence degenerates, you get a filtration on the homotopy groups of this, and then that's exactly. Right. Yes, I was told to repeat the question when people ask. So he asked, how does this give you property 1? So, yes. All right. So the guess is that this comes from topological K theory. In fact, there's a Chern map from topological K theory of C to periodic cyclic homology, and the lattice conjecture states. I'll just write it here. it states that when you tensor this map with C, or rather when you tensor K top with the induced map from the C linearization of K top, is an equivalence. So right, this is the lattice conjecture, and it's stated for C smooth and proper. Alternatively, you can view it as smooth and proper means that it's dualizable in this category of idempotent complete categories. So now I'm going to jump into.
Sorry, do we know for smooth and proper that K theory is connective?
For smooth and proper, that K theory is connective. Well, it'll always be a module over a periodic KU. So.
I mean the algebraic difference.
The algebraic.
I think it's the conjunction.
Yes.
So no.
No. Good question. Yeah, so the question was, do we know if the algebraic K theory will be connective for any smooth and proper? And the answer is we don't know it. So I'll just give a little bit of the state of the art on this, on this conjecture. Oh, I should say that when I took the K-theory presheaf in the definition of, and maybe this is already clear by the fact that from the Motivic definition, this K-theory presheaf, I'm taking the non-connective K-theory, not the connective K-theory. But originally there was two variants of the definition, but from the beginning, sort of, I'm taking the non-connective K-theory. All right, so I'll just say state of the art. So a key proposition or theorem proved by Blanc when he set forth his theory was the following, and I want to spend some time on this, because in some sense it justifies why this is called topological K-theory. So let X be a separated scheme of a finite type. And then there exists a natural equivalence. From K top, from perfect complexes on X to, with a KU cohomology of the space of complex points on X. And let me just, I'll actually just prove this because I think it's sort of, you get a good sense of how the theory somehow works. Question? Okay. Right, so first, if X is smooth, then this can be seen from the Motivic version of the definition, which I guess I erased, but this can be seen as follows. We have, we can write, I'll just start here. Right, this was the functor from idempotent complete categories into SHC. So now we're viewing this thing. This is a description of an object in KGL modules in Motivic spectra. So we can rewrite this as the internal hum from, again, if X is smooth. This is the internal hum in SH. Right, and then we apply a Betti realization to this to get Well, let me be a little pedantic now, because this is dualizable in SHC due to well, there was a number, I will not recall the names, but they were mentioned yesterday in Jonathan's talk. But this will be a dualizable object, so we can pull out the KGL. And this is monoidal, so it'll send. It'll preserve the duality functor in particular, so it'll send us to. And then this is actually going to just be sent to the suspension spectrum of the space of complex points of X. 1. And Betti realization of KGL, as I said before, is KU. So right, because this is dualizable now, you can pull the KU back in. So, and this is exactly KU cochains, KU value cochains on this space. Okay, and in the general case, Blanc shows that there's this natural map is a map of so satisfies CDH descent. So it's a map of CDH sheaves of spectra in the CDH topology. By what I just said, this is locally an equivalence, so it glues together to a global equivalence. So for an arbitrary separated scheme of finite type X, which is not necessarily smooth, you can conclude that this is an equivalence. So, all right, locally, an equivalence by the above. All right, and so in particular for these, so for X, C equals perf X, and in fact we don't even need smooth and proper in this case because X is arbitrary separated scheme of finite type. The lattice conjecture holds. Since, right. The periodic cyclic homology, well, this is just the two periodicized de Rham cohomology. Which is, well, also two periodicized singular cohomology. Well, let's write this way. And complex K theory, when you tensor with Q or C or something, then you'll recover this. You'll recover singular cohomology. Right. So more recently, let me just point out some work of Konovalov. Some more examples of the lattice conjecture. So this is a nice structural result, proven not for topological K theory, but for the semi-topological K theory. So before you invert this bot element. So the result is the following. So
what's the assumption on X in this theorem? Just the latest theorem.
X is separated a scheme of finite type. So in fact, you get this lattice conjecture. The category is not necessarily smooth and proper in this case, but you still.
How, I mean, this HKR, your first step, you solve HKR. I'm confused to whether the probability to access singularity.
Ah, right. Oh yeah, and it still agrees with this. Yeah. So right, you have a nilpotent extension. This means that it's a surjection on pi 0 with nilpotent kernel. complex DGAs. Then the induced map. From the semi-topological K-theory. Is an equivalence. So it's a nil invariance type result. And as a corollary, if B is a connective proper DGA, then the lattice conjecture holds. So right. And using this, one can extract more concrete examples of this, this lattice conjecture. So for example, for derived schemes, such that the truncation of the derived scheme is separated of finite type, then you can conclude. And also for various examples of group algebras where where the group is not necessarily even finite. I think connective means that it's, well, pi 0 does not have to be 0. I think.
I see, but you don't mean like connected. So how do you deduce the corollaries now?
Well,
if pi 0 of B is commutative,
mm-hmm.
B is connective and pi 0 is commutative, then I see that the corollary follows no trivial statements.
Maybe.
No, it's proper, so it's commutative and time dimensional.
Sorry?
We also know that it's connected and proper, so if we throw away the positive part, then it will be time dimensional. Yeah. And since then after throwing away the importance, it's very clear to find some
Yeah, this is his result, so maybe I defer to him. But yes, okay, right. Okay, let's jump now to right. So, as I said, this allows you to conclude for derived schemes where the classical truncation satisfies the properties before, or yeah, various examples of group algebras. And I think there are more examples too. But okay, now let me introduce the notion of relative topological K-theory, which I had introduced a while back. Right, so let me use this notation. So if you look at, right, we use this notation. Define, so if you look at perfect complexes on a scheme, this becomes, this is symmetric monoidal. So you can view it as an E-infinity algebra object in idempotent complete categories. So this notation just means modules over that. So, right, so construction / proposition was that there's a relative version, so there exists which is also localizing, but not valued in spectra, as you'll see. From this category to sheaves of spectra on the space of complex points. right, such that the following are true. So this is one. The topological K-theory of the unit, so of perf x in this case, is just right. This sheaf, which sends an open set V to KU cochains on, U to KU, V to KU cochains on V. The following property, if we have a morphism of schemes, then K top of this gives perf y a perf x linear structure. So you can apply this functor to it. And you can identify this with a push forward of the sheaf of spectra, this sheaf of spectra on the complex points of y. So it's just, right, it's just. I mean, yeah. At the time, this was just like a sanity check that this holds. But actually, this property is nice because using 2, one can often obtain canonical variations of Hodge structure structures. Sorry, in the classical sense, not this non-commutative Hodge structure. At least when so over X over this space. At least when X is when the category is admissible. I.e., it sits in a semi-orthogonal summoned I'll just write it this way. So this sits as a semi-orthogonal summoned of perf y in a perf x linear way. So semi. Essentially, because this will be a locally, and I'll revisit this theme in a moment. This will be a locally constant sheaf of spectra, so you can view it as a local system over X. So then for any semi-orthogonal summoned of such a category, you'll also get a local system.
You said what are the assumptions on F?
On F. It's an arbitrary map of schemes, yeah. But I should have said for X, quasi-compact, quasi-separated, to define this relative, yeah. So.
But you also need the complex points. Maybe you need more.
Well, no, you can still take the complex points of X, and then you're going to look at, maybe you would want to look at finite type over X, maybe, but.
No, I mean your analytic topology is.
I mean, what's the objection that this will be that you?
No, just I mean you might have infinite dimensional space and
Oh, yeah. Well, I guess in that case, yeah, maybe. I didn't write down the hypothesis, but maybe relatively separated finite type over X. I'll leave it like this, but yeah, I can look later. I don't remember now. Okay, so right, and this relative K-theory has been used in work by, for example, Alex Perry to study a categorical variant of the integral Hodge conjecture, but for categories, so it's right. Just a little plug. All right, so now I want to describe an application of this relative K-theory towards a computation of the topological K-theory, defined by Blanc of Azumaya algebras, which thankfully briefly were touched on in Marco's talk. So yes, as we saw earlier today, an Azumaya algebra, say over a ring, although I'll always be working with derived Azumaya algebras. So setup. So the setup is a derived Azumaya algebra. I'll put this in quotes. Over a scheme. So let's say over a ring. In particular, this means that this canonical map is an equivalence so it's an algebra object in mod R such that this map is an equivalence, and it's a compact generator as well. Right. Another way you can, and as we saw, another way you can view this is that if you take modules over this algebra, then this is an object in PIC. This is an invertible object with respect to the tensor product on compactly generated. This means compactly generated R-linear stable infinity categories. Right, and so these glue in the étale topology so you get a sheaf of such objects. So you get a sheaf of algebras which are locally equivalent to, at least in the non-derived case, they're locally equivalent to matrix algebras. Okay, and the idea is that the idea of this computation is that topological K-theory. So you can look at modules over such as my algebras. This will be a C-linear DG category, or in particular a perf X linear DG category if you're working over a base scheme X. So that topological K-theory should send, well, yeah, I don't know why I'm writing this, but it should send Azumaya algebras to twisted K-theory, to twisted topological K-theory. What is twisted K-theory? I will just give a very gentle recollection. So for a space or an infinity groupoid, we have a map. We start off with a map from B. Like now we're viewing it as an infinity groupoid 2, the Picard. Now I'm only working with KU now, so we'll talk about twisted KU cohomology. So You can view this as just a map of these are both spaces, but technically, yeah, we want to view these as infinity groupoids or infinity categories. So we can compose with this fully faithful embedding into KU. Right, this is the space of invertible objects in this category. This category is complete, so we can take the limit of this diagram. So essentially, we define KU alpha B to be the limit of the composition, which I'll denote as alpha tilde, indexed by B. Right, and this is will be an object in KU modules. In particular, we can view this as global sections of the associated of a locally constant sheaf of KU module spectra. All right, so the statement is the following. So let X be and then OA, again, it could be a derived Maya algebra. Then the K top, the sheaf of spectra that you get by applying this topological K theory to this category. It's kind of an awkward way to write this, but this corresponds to a local system or a parametrized spectrum. So when I write XC, I'm implicitly taking singular chains and viewing it as a Kahn complex. This maps to pick KU, right? So in particular, this is a locally constant invertible sheaf of spectra. So it corresponds to an object like this. And in fact, you could take global sections and you get the twisted K theory. Right. It is a locally constant invertible sheaf of spectra. And as a corollary, at least when as a corollary, this is true when you forget the X perf X linear structure. So for Blanc's original invariant, you get perf A, perf OA is equivalent to this global section. So it's equivalent to KU alpha all right. And now I'd like to jump into one last section of the talk where I kind of like throw in some equivariance into the story. So the point of this discussion is that, right, so some history, this semi-topological K theory, it was not originally defined just for schemes, say, quasi, maybe even, with restrictions. Right, this was a functor on schemes, and then this was an invariant by, defined by Friedlander and Walker. So semi-topological K theory goes back to Friedlander and Walker. In later work, they proposed a theory for for real varieties. So varieties over spec R, and which should interpolate between algebraic K-theory and Atiyah's real K-theory. In the sense that there's a map from the algebraic K-theory of X, right? X goes to spec R. There's a map from K of X to this definition, this KR semi-topological. Right, so this is an invariant of spaces with an involution. So if you start off with a real scheme and you take its complex points, then this inherits a C2 involution. And this is an invariant of right. So this measures complex vector bundles over this space, which are such that the structure map, the projection map, is C2 equivariant, and sorry, E. This has to also have a C2 action. This map is just supposed to be C2 equivariant, and the induced map on fibers is C antilinear. So these are real bundles. Bundles with real structure, I guess. All right, so in this proposal, they proposed a C2 equivariant version, but they stopped short of providing a definition due to the lack of equivariant technology at the time. So I will now describe a C2 equivariant version, but not of the semi-topological K-theory, but of the bot-inverted version, so of topological K-theory. And it follows this Motivic picture. Right, we work over SHR, then we still have this Betti realization. But now this lands in genuine C2 equivariant spectra. I believe this was studied by Heller. Ormsby. Right, so this is a C2. So this is a C2 comes from the Galois group of C and R. Okay, so and it has the property. This Betti realization has the property that right. This is. You can pull back to Motivic spectra over C. You can take Betti realization there, and this commutes with taking forgetful functor. So we can define very simply for C in ket R. We can define KR of C as the Betti realization of the complex over of KGL of C, and this is a C2 spectrum. Right, the same thing as before when you have this functor from DG categories to non-commutative motives, and then to commutative motives or Motivic spectra, and this is the notation I use for the KGL module in R linear motives, and you apply this Betti realization there. And again, on object, so underlying object of this will just be K top of C tensor over R with And now let's try to get a handle, and I'll be quick, on the fixed points of this. So like, why am I even proposing this? So the proposition, right, so first let me state quickly a theorem of Karoubi, which says that if X is a real quasi-projective variety, then we have this map from the KR of the complex points of this will just be the naive C2 fixed points of the complex points. Note that complex points of a real scheme will be the same as complex points of the base change to C. So, okay, so right, this side is the aperiodic Atiyah real K theory of X, the complex points. This is what you expect it to be. So right, this is aperiodic as a Z-graded cohomology theory, but as an ROC2, which is the natural grading for. So as a ROC2 graded cohomology theory, it means that you're grading on the on representations of C2. So there's two. There's the trivial one and the sign representation. So this makes it 1-1 periodic. But here we're just viewing it as a naive spectrum. So it's just this is the aperiodic variant, right? So the proposition that I want to give is that, and I'll end with this. Yes.
Why do you need quasi-projective here? Isn't it just, I mean, this is the C2 spectrum and the geometric fixed points plus Tate are zero because they are modules? Or?
Yeah, you're probably right. I was just quoting the original statement. Yeah, I don't think you. Yeah. First, I give too little restrictions, and then too many restrictions. Okay. Anyways, right. So this is the homotopy fixed points. So the proposition is that you can identify even the genuine fixed points in this case, that for perf X. And essentially, this follows from. No. You have this the following Pullback square of spectra from the genuine C2 fixed points to the geometric fixed points to the Tate. The homotopy fixed points. And right, essentially, yeah, this is the Tate fixed points, and this will actually be a map of right. So so by work of I wrote this the Tate C2 of KR. This can be. So KR is now a genuine C2 equivariant spectrum. So Tate fixed points of this vanishes by work of, and in fact you can apply to KR. This will be a ring map. So in particular, you can conclude that the geometric fixed points vanish. So this will be the zero map. In particular, the genuine fixed points are equivalent to the homotopy fixed points. So in some sense, this is at least for when you apply this to perf X for some scheme X, then this is a Borel equivariant theory. But it'll be nice to understand what, for general non-commutative inputs, what this looks like. Right. So we obtained a periodic and non-commutative version of the sought-after real K theory of Friedlander and Walker. And I'll end here.
Any questions for Tasos?
In this twisted case, so do you know if the lattice
I think you can state the parametrized lattice conjecture. I don't think it's any easier necessarily.
No, so I mean
Oh.
specifically this
So Azumaya. Oh yes, and well, okay. So in the non-derived setting, any Azumaya algebra will, like perf of any Azumaya algebra will sit as a semi-orthogonal summand of some scheme perf y over some scheme y over x, and in this case, yes. So yes. In that case, yeah, it holds.
What does that theorem in fact say? Like, where is the input of the Azumaya algebra on the right?
Yeah, I was being a little fast with this. So there's two ways you can view it. There's actually a functorial assignment induced by topological realization from essentially Azumaya algebras to these twists. So essentially, this follows from the fact that, right, I have this functor. And when I apply it to this category, like this, the real statement is that this is locally constant, and I wrote it locally constant and invertible. Locally constant and invertible. So in particular, there's I can canonically identify it with, right, so there's an equivalence of categories between locally constant sheaves of spectra on a space, with, well, I guess let's assume B is locally contractible, I guess. I think it's even weaker than that, but right, functors from, I guess, right, sing B to spectra. And actually, this is compatible with symmetric monodal structures too. So right, you get an object here which is locally constant. In particular, it corresponds to an object here, and it's also invertible. So in particular, invertible means that it'll factor through this Picard space. Well, I guess here we're looking at mod KU. So you get this twist that then I used here to define the twisted K theory. Another way you could view it is that there's in algebra, there's a stack in algebraic geometry that parametrizes these Azumaya algebras, and then if you take the realization of this stack, I won't. Let's see. Well, it's the KGM 3 times KZ KZ1. I'm forgetting an extra term, I think. But if you take the realization of this stack, then you get a KGM2, yes. If you take the realization of this stack, you get a KZ3 factor, which this is oftentimes you can twist K theory classes by maps to KZ3. So, right. So you're looking at there's a map from X to this from the scheme X to this Brouwer stack, and then if you apply realization to this functor, to this map, you get you get a class that you can use to twist KU with.
No more question? Okay, so we continue at 3:15, and let's thank